So most of you are probably familiar with this. You've run across it at some point or another. Definition. Let G and H be your favorite pair of groups. A function F of G to H is called a homomorphism if we satisfy this. So this comes from root words, homo meaning same, and morphism being change, right? So what do I mean by same change? Well, actually, for all x, y. So let me be a little bit more precise here. If so let me distinguish between the operations. We'll call the operation in G circle. We'll call the operation in H star. Then what this really means is the homomorphism has to give some respect, right, to do the same change. F operating on the combination of X and Y as elements of G is F of X, Y. But see now, these two animals are in H. So respect to the operation on that. Let me give you some more fun adjectives that we stick to this. Suppose F is a homomorphism. And to be specific, F from G to H. If F is 1-to-1, that is 1-to-1 as a function. You say that is a monomorphism. Or maybe I'll say injective homomorphism if I'm not just a brevity thing. If F is onto, you say that is an epimorphism. I feel like I'm teaching languages now, right? Because of all these really cool root words and all this epim means onto and so forth. Or we might say it's an onto homomorphism. If F is 1-to-1 and onto, F is an isomorphism. And in a certain sense, it means that these two groups are essentially the same, because not only do we have respect going on with the operation, but there's a 1-to-1 correspondence between elements of the group. And if F is an isomorphism, and G equals H, then F is an automorphism. So that's kind of even more specialized than isomorphism. Automorphism means it's 1-to-1 and onto from the group to itself. These are actually quite important. We'll see a lot of examples of that coming up. Okay, I'm gonna give you a couple of properties here. example, just kind of a neat sort of consequence. I won't do this out of order. I'm gonna sort of pull 239 out of the blue, and then I'll go back. Suppose and let me say, whenever I say homomorphism, what I'm going to mean is that the domain and the codomain are actually groups, right? So it's going to be implicit, even though I didn't explicitly say that here. Here are some properties of homomorphisms. F of the identity of G is the identity of A. So any homomorphism, any good homomorphism has to take the identity and domain, the identity codomain. B F of x to the n power is f of x to the n power for all n and z. Here I'm writing both operations, G and H as multiplication, but for example, if the operation over here in H is addition, this would translate to f x to the n is n times f of x. C is 1-to-1 if and only if the kernel of f, which is the set of x and g, such that f of x is the identity of H, is the kernel of f, which I've defined here. This is everything in the group that takes everything in the group, the homomorphism takes the identity. This is called the kernel. You all have heard the word kernel before in pre-exam. Of course, you probably heard it in linear algebra, right? Sometimes they call it the null space. That's exactly what's going on here. What happens in the null space? In the vector space, it's everything that takes that kills all the vectors, right? It takes them to zero, but zero is the identity of the vector space, right? As additively. And this is actually really cool because homomorphisms have so much structure that to tell whether it's 1-to-1, you don't have to go through all that crap of f of x equals f of y and try to prove x equals y. All you have to do is look at the kernel, which is kind of cool. I think I'll show you that one. D, f is onto. If and only if the image of f, which is the set of f of x, where x is g, is all that. That's not too exciting. I won't bother to prove that because this is no different than a map of sets, right? There's nothing special about being proved there. And E, F is an isomorphism. If and only if there exists homomorphism G and HG such that one of the FG, it is the identity on H, and then GF. By the way, let me point out that this one's not a surprise either, because you guys, from basic kind of function theory, if you have a 1-to-1 and onto map from G to H, then it's got an inverse, right? G, and that's what this is. It's just the inverse that takes everything back. The one surprising thing about this is the fact that the inverse actually still turns out to be a homomorphism. Right? I mean, okay, the inverse function, maybe it's not clear that it satisfies the homomorphism property, but it does. Okay, so let me do a couple of these. I wanna do A and C, and I'll leave the rest for exercise. Okay, so we want to show that it takes the identity. This one's kind of cheap. So well, let me call it H. I'll be descriptive. I don't know much, but I know it goes somewhere, right? I noticed that H times H equals F of B. D. But this is a homomorphism. So this is F of G squared. I don't know much, but this is still the identity. It's H. So what do I get? I get H times H is H. Now I'll multiply both sides of this equation on the left by H inverse. And I get H is the identity. And there you go. So you got to take the identity to the identity. Any questions on that part?
I have a question just on the one before. When you have like FG equals 1H, is that the same as, sorry, on the chalkboard before?
Oh, right
Is that
here.
the same as EH?
Oh, that is. Thank you. This is a function, and what I mean by this is the function from H to H. 1H. It's just the identity function.
Oh, okay.
And the same for this. Okay, other questions? Okay, let's look at, because it's so dang useful and cool, let's look at C. So the claim here is that F is 1-to-1 if and only if the kernel of F, which is everything in G that's nuked by F, takes it to the identity, is the identity. So let's try. So what we have to do in this direction is prove that the kernel of F is the identity. By A, the identity is contained in the kernel of F. Right? Because we've already shown that the identity goes to the identity of H. So really, the only thing we have to show here is the other direction. Now, suppose containment. Suppose X is in the kernel of F. Right? So F of X is the identity of H, but this is F of G as well. Therefore, X equals G. And there you go. So now everything that's in the kernel has to be the identity of G. But okay with that? What you done so far? Okay, so how about the other direction? For the other direction, we're assuming that the kernel of F is the identity. And now we want to show that F is 1-to-1. This is really kind of a more interesting direction. What we need to do is we need to show F is 1-to-1. And so I want to take kind of the classic definition here. So suppose F of X equals F of Y. And here, of course, X and Y are elements of G. Okay. Well, so what can we do with this? Any idea? Okay, right. So let's do this. Basically, I multiplied on the right, I have y inverse, that's a good element of H, right? Y inverse is in G, so I can do that with y inverse. And so this becomes f of x y inverse, y inverse, of EG, H. Right? So what does this mean? Well, I don't know much, but if I look at this little equation I've got here, this means f of x y inverse ends up being the identity, right? So by definition, when I plug x y inverse into f, I get the identity. That means x y inverse is the kernel. But the kernel of f is assumed to be the identity of G. So x y inverse G. Now I'm going to put both sides by y, and x equals y. So f. Any questions on that? How many of y'all are teaching anything this semester? What you got?
Math 1020,
10-20, like a.
or 1020, so the business California.
How about y'all?
Math for
10-20? Where do y'all start in that class? You tell them about the exponential and the log?
I started with relations and functions, going over those concepts. And
Let me tell you how not to teach exponentials and logs to refresh. Okay? But I will teach it to you. Here's an example. Consider groups. So I mean, the positive reals under multiplication. So let me kind of talk you through that. What do we have here? We have the positive reals, everything on the interval from 0 to infinity, not including 0. Right? What happens if you multiply two positive reals? Positive real. What's the inverse of a positive real? Alpha, 1 over alpha, which is also a positive real. This is a group under multiplication. Here's another one. Reals under addition. Okay. Now, let me give you an old familiar function. Consider you might remember that what happens with the natural log, the domain has to be the positive reals, right? And when you plug it in, you can get any real number. And note, for all, let's say x, y, the positive reals, natural log of x times y is the natural log of x, natural log of y. An oldie but goodie, right, that maybe causes a lot of consternation among the freshmen, but there you go. So natural log is a homomorphism. Probably bad idea to go in there and say, theorem, natural log is a homomorphism from positive reals under multiplication to reals under addition. Right? That will not do wonders for your course evaluations. Might not even help mine. So let me give you kind of an interesting consequences. This is a group under multiplication. What's its identity? The identity is 1 under multiplication. How about this? The identity is 0 under addition, right? So consequence. Natural log of 1 is 0. Always, because it has to take the identity to the identity. All right, that's kind of, you know, you may have never seen it derived that way, but the reason the natural log has to be 0 is because it's a homomorphism. Right? There's one going back. There's a homomorphism going back because e to the a plus b is e to the a, e to b. Right? And e to the 0 must be 1. So there's kind of an application of homomorphisms, just you know, something ordinary that you've seen before. Let me give you a couple of examples here. More homomorphisms. So 1, let's let n greater than 1. Then z and z mod n. On phi k, take your favorite k and be k bar. Right. So for example, what do I mean? I just mean whatever this k is reduced with mod n. Are you all familiar with what I'm talking about? So for example, 0 goes to 0 bar, and n goes to 0 bar, and 2n goes to 0, and so forth. This is a surjective homomorphism. And anybody want to guess what the kernel is? Remember, the kernel is everything that goes to the identity here. What ends up going to the identity from C to Z n? Okay, good. Multiples of n. So it's got a big fat kernel, right? It's just every multiple of n goes to 0. 2. Consider the function let be groups. Consider omega h given by this function is always 1 to 1. Right? Because Actually, let's just let A, but I want this to be a homomorphism. I want this to be not A. This is 1-to-1. Because if F of A equals, if FA1 equals FA2, then A1 inverse equals A2 inverse. And by uniqueness of inverses, as we discussed last time, this implies A1 equals A2. So certainly, this is 1-to-1. It's also long to it. You need somebody to explain what it's on to?
Every element has an inverse.
That's exactly right. So, A, then A, then F, A inverse. Alright, so, right, because every element has an inverse. So, everybody agree with that? However, this is usually not a homomorphism. F is a homomorphism if and only if that's exactly right. Yeah, and the arrow works both ways because in general, you don't expect the inverse of A1, A2 to be A1 inverse A2 inverse, right? You need a abelian to make that work. So the interesting thing about this math is it's always 1-to-1 and onto, but it's only a homomorphism and therefore an automorphism if and only if A is abelian. Here is another type of homomorphism that is. So in example 2, to make this interesting, to make the motor go, I need A to be abelian. Here's an example we don't want A to be abelian. See, let S and G define phi of X for G to G by so notice that let me show you how group theorists, they get so much mileage out of this. Well, method of the sleeve, and this is so this is a homomorphism. But what happens if, and in fact, you can check this one's also 1-to-1 and onto. Can somebody explain to me why this is kind of boring if G is an abelian group? Yeah, sure. That's right. Because what happens is if G is an abelian group, then the XG can be turned around, and this is just phi XG equals G for all G. So it's just nothing. Right? If it's not abelian, this is very useful homomorphism. And in fact, what you really want is you want X to not be in the center of G. So you want there to be something in G that X doesn't commute with to make this interesting. Of course, it always works. It's just sometimes it's always the identity. Definition. group. Subset. I should say non-empty, but it'll be obvious after I finish this definition. H and G is in subgroup. Yeah. Is a group under G's operation. And sometimes I'll write group theory, so I can do this, like a little less than or equal symbol to denote subgroup. So what is a subgroup? It's just a baby group inside the group. Every group has two sort of obvious subgroups. Can anybody tell me what they are? The group itself, right, and the identity. And these are usually different subgroups. So the idea is, of course, the subgroup is just a smaller group inside a group. Example. Number one. See, under addition. Anybody name? I mean, obviously, one subgroup is the identity, and one subgroup is all Z. Anybody know any others? The evens. The multiples of 8675309, honor of Tommy Tucumb. Can I parameterize this? Okay. Yeah, actually, Z is kind of cool because I can actually in closed form tell you what all the subgroups are. Here's an exhaustive list. They look like this. When n is 0, this is the identity. When n is 1, this is the whole thing. When n is 2, this is the evens. And when it's 8675309, actually, this is an entire list. It may not be obvious at this point, but see if you can convince yourself that those are, in fact, the only subgroups. And I'll give you a hint. The Euclidean algorithm will help you out with that. The rationals under multiplication, or I'm sorry, under addition, is more complicated. In fact, one subgroup is Z, right? And you've got the activity, but you also have all kinds of other things. By the way, what happens if you take two fractions and they both have odd denominators and you add them together? What can you say about the new denominator that you get? 1/5 and 1/7. It's still odd. Do I agree with it? So if I take two fractions, A over B, and they both have odd denominators, when I add them up, it will still have an odd denominator. Right? The identity is 0 over 1, ding, ding, ding. And everything has an inverse additively. A over B is inverse is minus A over B. And if B is odd, then B is odd. So this is actually a subgroup. Very complicated though. And in fact, there are infinitely many subgroups of this, and they're much harder to list. Some of them are finitely generated and some of them are not. But in fact, every finitely generated subgroup can be generated by a single element. Let me give you another example. Here's a couple of groups of order 6. And this is kind of warm up to another theorem we've got. Okay. Okay, let me see if I can list all the subgroups here, and you might verify the details. Z6 is easier to verify. One subgroup is 0 bar. One subgroup is Z6. Okay, so I got the easy ones, right? The identity and the whole thing. Do I see any other subgroups? Any subsets that form a little baby group inside this group? Here. Okay, I'll buy that. Anybody see any others? Any others? There are no others, right? You might ask, well, what happens to name 4? Well, 4 and 4, if you take 4, it's got to have 4 plus 4, which is 2, and so forth. All right, so we've kind of already done that one. Now, let me point out something. How many elements, what's the order of Z6? 6, right? Look at the order of the subgroups. What are they? 1, 6, 3, 2. What do those numbers have in common? They all divide 6. This is not a coincidence. Anybody think of another group of order 6? That's right, the symmetries of the triangle, or yeah, so you thought of it in terms of D3, right? Symmetries of the triangle. That's also the same as S3. By the way, that's the largest number for which S3 and D3 coincide. Let me write the elements out. This. Again, there's 6 elements, 6 symmetries of the triangle, or 6 bijections from 1 to 3 to itself, whatever you like. Now, there's the big one, right? The parent of them all. Here's the identity. Smallest one. Now, there's actually a subgroup of order 3. And it looks like this. Notice there are 3 elements here. Notice these 2 are inverses of each other. So it's pretty easy to check this through. Just like this one had one and only one subgroup of order 3. This also has subgroup of order 2, but it's got 3 of them. So you've got E12, E13, and E. So as opposed to the previous example, where for every divisor there was one and only one subgroup, here you have a subgroup for every divisor, but for the divisor 2, you've got 3 of them. There's 3, it splits out into 3 groups. Now, I don't want you to jump to too many conclusions here, because what seems to be true, and we're going to actually prove this theorem, is if you have a group of order n, it turns out that any subgroup must divide, the order of any subgroup must divide that n. This begs an obvious question. Suppose that you have a divisor of n, does that mean that you have a subgroup? The answer is in general, not necessarily. For example, how many elements does S5 have? It's like, yeah, 5 factorial, which is 120. Both 30 and 40 divide that number, but S5 has no subgroups for either 30 or 40. Right? You also don't necessarily have a unique subgroup that'll work. It's actually going to turn out that the groups that are cyclic, that is groups that are generated by one element like this one, that's always true for. It's got a subgroup of every divisor and only one. But in general, that's not true at all. Okay. Let me give you any questions. I'm going to give you one of my favorite little theorems here. This is called the subgroup criterion. Let G be the group. H and G in our next subset. So suppose I walk up to you on the street and I give you a subset of the group. I'm going to assume it's not empty. And you might say, oh, how can I tell this is a subgroup? Well, you could check all the group axioms. But here's a shortcut. H is a subgroup of G. It can only have for all X, Y, and H. That's Y inverse. This is because basically this has all the group stuff wrapped into one little neat package. So I totally dig on this because there's only one thing to check. Check that if you have X and Y in that subset, that X, Y inverse is in there. If that's true, it's a subgroup. This direction is not very difficult to prove because if H is a subgroup, if X and Y are in H, then Y inverse is in H and the product's in H. This is just follows. The interesting part is the other arrow, because the other arrow says, hey, that's all you need. All right. Let me point out, let's go through this. Suppose we have this property that for all X, Y, and H, that X, Y inverse is in H, right? Suppose that we've got this, right? Let X be in H. And it's subtle, but there's where I've used the fact that H is a non-empty subset, right? When I have that H is a non-empty subset, I know there's at least one little piece of garbage in there. So notice that X and X are in H. Therefore, X inverse equals the identity is in H. Ding, ding, ding. Right. I mean, nobody said X and Y had to be different, right? So what we've shown so far is if X is in H, then its inverse is in H. Or I'm sorry, what we've shown now is that the identity is in H, right? Now, if X is in H, we know that E and X are in H because we've already proved that E is there. Therefore, this plays the role of X, this plays the role of Y. E X inverse equals X inverse is in H. Now we've got inverses, right? Finally, if X and Y are in H, then Y inverse is in H by previous. Because we've already shown that the inverse of anything is in there. Therefore, X, Y inverse are in H. So X, Y inverse, inverse. So we now have closure. So we've got products, inverse, identity. We're good to go. The only thing we're missing is associativity. Somebody tell me why I can skip associativity. Right. Associativity inherited. Because you know that the associative operation works for everything in G, and H is a subset, so it's going to work. That's right. Okay, so let me give you the following proposition. This proposition actually, most of it I'll leave as an exercise. It gives you, this is sort of definitions as well. I'm going to give you some examples of groups that show up in these propositions. My setup is F from G to H is a homomorphism, and A is a subset. And let me emphasize data have to have any special property, it's just some non-empty subset. A, the kernel of F is a set of X and G, such that F of X, the identity of H, is a subgroup of G. And in fact, it's more than just an ordinary subgroup. We'll talk about that later. The image of F is F of X is a subgroup of H. CG, which is a set of C and G, such that CG equals GZ for all C and G. So this is basically, this is all the stuff in G that commutes with everything in G. This is a subgroup of G. By the way, there's always at least one thing in here. Can you tell me what it is? The identity. So that's a good indication that maybe it might be a subgroup. This is called the center of G. D, CGA. This is the collection of everything in G that commutes with everything in A. GA equals AG for all A and A. And this is the subgroup G, and this is called the centralizer of A and G. And one more, and that'll be it for today, is the famous normalizer. This is actually a generalization of the centralizer. It turns out that the normalizer contains it. This is a set of G and G such that G inverse and G equals A. And what I mean by that, let me clarify what this means. This is the set of things it's the set of all, and these things are called conjugates. This is the set of all conjugates. So you just go through everything in A, you list this, it makes a set. If this turns out to be the same as A, it might move things around, but if as a set, it's the same thing. This is the G is in the normalizer. And this is a subgroup of G, and this is called the normalizer. So I think that should probably wrap it up for today. We'll finish off this section really quick. You might want to take a quick look at it and we'll get on into subgroups and whatnot next time, or cyclic subgroups. Any questions? Cool. All right, well, let me know if you got any problems with the homework or anything. Other than that, you guys have a great day and we'll catch you on the flip side. Any questions out there? You guys good to go? All right. See you folks next time.